Hello, I'm Hassan Mortagy, a PhD student at Georgia Tech. I will summarize our paper titled Walking in the Shadow, a new perspective on descent directions for constraint minimization, which will appear in NeurIPS 2020. This is joint work with my advisor Swati Gupta and Sebastian Pokutta. In this paper, we consider the problem of minimizing a mu strongly convex and L-smooth function over a polytope P. There exist two main paradigms to solve this problem. The first is a class of methods known as Frank-Wolf variants, which assume access to our polytope P via linear optimization oracle. These variants are very efficient, however, they are prone to suffering from slow convergence rates. On the other hand, mirror descent variants assume access to P via a projection oracle, which is more expensive than linear optimization. However, these algorithms have optimal convergence rates in the sense that they don't depend on the geometry of the problem, nor the dimension. In this paper, we demystify the impact of movement in these descent directions towards attaining constraint minimizers. In particular, we ask, what would be an ideal direction of descent, and how can we unify existing theory on descent directions for constraint minimization? We start answering that question by defining the shadow of the gradient, hence the name of our paper. So for any point x in the polytope, the shadow of the gradient at x is the directional derivative of the projection operator at x with respect to the negative gradient direction at x. So why do we care about the shadow of the gradient? Because we show that it is locally the optimal direction for descent. In other words, it is the analog of the negative gradient in unconstrained optimization. Furthermore, for any point x0 in the polytope, we define g of lambda to be the projections curve at x0 parametrized by the step size lambda. We show that this curve is piecewise linear. We have an example here on the slide where the projections curve is the orange piecewise linear curve with breakpoints xi. We also show that we can trace this entire projections curve iteratively as follows. So given a breakpoint xi minus 1, to compute the subsequent breakpoint xi and the next linear segment of the projections curve, we just need to consider the gradient at x0 and note that we're not changing the gradient here, and we compute the shadow at xi minus 1 with respect to that original gradient direction. And then we do a line search for feasibility to obtain the next breakpoint xi and the next linear segment of the projections curve. We now use our shadow and parametric projections framework to unify various existing results on descent directions in the literature. So first, by construction, the projected gradient descent step lies on the projections curve, which we know how to trace. We also show that the same holds true for the Frank-Wolf vertex. In particular, when the Frank-Wolf vertex is unique, it forms the endpoint of the projections curve, thereby drawing a novel connection between projected gradient and Frank-Wolf methods. Also, a nice property is that the shadow of the gradient gives a true estimate of primal gaps. Finally, we note that we can use our framework to obtain optimal away and pairwise steps used in Frank-Wolf variants. We now propose two algorithms. First, we have the shadow walk algorithm, where at every iteration, it traces the projections curve using iterative line search and shadow computations until we have sufficient progress. However, entering this trace procedure every iteration can be expensive. So in the shadow CG algorithm, we propose adding Frank-Wolf steps which are efficient to compute, while also forming the endpoint of the projections curve. Thus, the greed of these steps can help us potentially avoid entering the trace procedure every iteration, which makes the algorithm more efficient. So in each iteration, we either take the Frank-Wolf direction, which is the green direction we have in the figure here on the slide, or we trace the projections curve, which is the yellow curve. So now we have a table that summarizes various existing CG variants and their convergence rates. The key takeaway is that the rates of CG variants depend on geometric constants, which we do not have. Instead, our rates depend on a constant beta, which is the number of breakpoints the trace procedure visits. This constant is invariant to any geometry deformations, preserving the facial structure of our polytope P. So our rates smoothly interpolate between the rates of CG variants and PGD. Thank you.